binary trees. So binary tree would be like this. The first node in binary tree is called root, and it has left subtree. So left hand side, it would be having the left subtree. Again, this is again another root, another tree rooted at this node. Okay, similarly, you would be having on the right hand side one more subtree, binary tree rooted at this node. So this one you can call left subtree, and this is right subtree. So you would be having one root, and the root would be having left pointer, which is pointing to the left subtree, and right pointer, which is pointing to right subtree. If you see the node structure would be like this. Data, left pointer to left subtree, pointer to right subtree. So I can say the fields are like this in the node. Left link, data, and right pointer to right subtree. So this is a node structure. In binary tree, any node should have at most 2 children. Means less than or equal to 2 children, any node at most. So if you want to represent this in a program, we have to design structures to or classes to represent this. We are going to define binary tree node class here. One is data. Node two more references to the left subtree and right subtree. Left and right. Let us write the constructor for this. So initially, you can set data is whatever you are getting, and left node you can set to null, and right node you can set it to null. So new class name is BT node, and if you say 1, what happens here? You are able to create dynamically memory the fields whatever you specified in the class. So here one node would be allocated here, n1 you are saying, with left pointer set to null, and data if you pass 1, 1, and right pointer is set to null. This one is n1. Okay. Similarly, if you create one more object of this class, again here what you are doing, you are able to create one more node n2 with data as 2, for example, with both the left and right pointers pointing to null. This is n2. So here we are able to create each node dynamically, but these are not connected. Actually, What is binary tree and what is binary search tree? Binary tree means this is the condition. Each node should have at most two children, 0 or 1 or 2. And binary search tree means in addition to this binary tree, you have to maintain one more property. All the values which are there on the left hand side for this any node should be less than. And all the values which are there on the right side should be greater than the root values. So if you see here in this diagram, root value is 10. All the values if you see in this subtree are less than this. And one more thing. So at each node that property should be maintained. For this node, if you have left and right, left hand side should be lesser. So this is 7. It is 6. Yes, it is maintained less than. And it is 9 maintained. So the property is maintained here. Properties, is it maintained? Yes, left hand side it is maintained. Right hand side 15. Left hand side is 12. Yes, that is less than. Right hand side is greater than. Yes, that is maintained. Means the property is maintained at this subtree. So for this, the property should be maintained at each node in this left subtree and each node in the right subtree. So then that is called binary search tree. So now let us try to look into the insert function in binary search tree. I want to create binary tree. Initially binary tree root pointer would be pointing to null when there are no nodes. That is step 1. So if you want to insert first, you have to create a node with data as whatever you are passing 10, for example. This is the first node you are going to insert in the tree. Then you have to allocate a node and mark both left and right subtrees as null. And you can, let us say this is P. Once P is allocated, root should come and point to the only available node. So let us try to represent this first. For this, we have to maintain root pointer, root reference across the tree. So binary tree, binary search tree, this is actually. So what do you want to maintain? Root, and create a constructor root equals to so if I want to create a binary tree here, B1 or B, new binary tree with empty arguments. Then what will happen? It will create memory to store the member root and that is initialized to null. So we got the picture, something like this. We are able to allocate root and we are able to initialize that with null. So if root is null, first allocate the node and make this as root. So what you have to check if, so let me write here. Insert routine, let us look into. So you are given or what do you want to insert? X. If R is null. Then what you have to do? So you can create a node P. How to create the node? We can make use of BT node. With X. And you can mark this as root. So we created a node P and root equals to P, we said. So then the picture is like this. So now I want to insert 7. Again, I need to call the function insert. What is the root value? Root, and I want to insert 7. Then you will come and check at the root 7 value. What is the value to be inserted? That is, let us say this is X. X value you have to compare with root data. Root data is greater than the X value. Be inserted on the left hand side. So means this link should be updated, is going to be updated. So then what you have to do is R roots left is going to be updated with what? You can do recursive call. So you have to insert here. Now what you can do is again call recursively insert at R left. Why we are inserting at R left? So we have to compare. If X value is less than R data, okay, then you are invoking this call. Okay, so we are doing through recursion. So we call through root. Root is this one, 10. So address of 10, root address means. And we went here in the first node and we checked it should be on the left hand side. So we are doing recursive call here. So now R value is changed to R left in the recursion. And we are going to insert the same as same value X. So our call would be like this. Insert. What is this is R. R left is null. And you are going to insert 7. When you invoke the call with this, whenever you see null, what we have to do? You have to create a node and you have to return the reference of that node. Return root. So if the R value is not null, means we are inserting the second node. What is the first condition we checked? If R X value is less than R data, then R left is going to be changed with what? Again call insert function with R left as the new root. In R left subtree X. So let us see what happens with this call. So you will invoke this with null. This is null. So what happens here? We create a new node. We create a new node. The data is 7. And this is P. For this node, this is root also. Okay. Then what we are doing in this call, we are returning the address of this. We should return the address of this node. After creating the node, we have to return root value. So that value, after creating the new node, we are returning the address to the previous call. So new node is created here and its address is returned in this call. And this is waiting on, R left is waiting on whatever the value it is getting, R left should be updated with that. So R left is returning, for example, this is allocated at 100 address, this node. This node is created at 400 address. You are returning this address 400. Now R left should be updated with 400. Means this should be 400 now, not null. Means this is pointing to this node. Similarly, let me insert 17, next number. Come here and compare the data. If the value to be inserted is x is greater than root data, then go and insert on the right subtree. So we can add one more condition here. Else, if x value is greater than or data, then you have to update or write. You have to insert new node in the right subtree or write and x value. And whatever the value this call returns, assign this to this one. So now let us try to insert 17 here. 17 come in, which is greater than, so that should be inserted on the right side. So this link should be updated or right with what? Do you one more recursive call on right. Right is null now. X. By seeing this call, what will happen? 17. So one more new node we would be creating here. 17. This is P, new node, and its address you are passing. So R right is updated with the address of, for example, this one. New node address is 500. This node's address would be updated with 500. So R right is modified with address of 17. So let us add that. X value is greater than root data. Then you have to do insertion on right subtree. Just try to insert one more node. 15. What happens here? You will come here, compare, and you should go on insert the right side. So the next call would be insert and address of the right subtree on 17th address, 17th node. And what you are going to address, insert 15. So actual first call is insert at 10, 15. By seeing this, you move to right side, next call. By seeing this, so 17 and 15, 15 is lesser value, so it should go on the left side. Left side is null, so there you will create a new node, 15. And 15, for example, it is allocated at address 700. Okay, this 700 address would be returned by this recursive call. This R left is waiting for the address, so this would be updated with 700. Left field is updated with 700 address. So just for consistency, we are returning the address of at this level, the address of this node to the previous one. Okay. And finally, we are returning the address of the root. For example, this is allocated at 300. So insertion finally returns the address of the root.